record on this computer. Okay, I think we're recording. I get the little dot. So we can go ahead and get started. Hello, thank you for coming to the QCSD's QC hardware workshop. Yeah, we're going to be talking about quantum computing hardware as much as we can in the hour that we have. Just before we get started, I'd like to note that because of the nature of this presentation, we'll be going into some detail regarding some of the the current QC hardware. And there won't be any math, but there will be some kind of abstract discussion of quantum mechanics and some jargony terms thrown around. I've done my best to sort of plan out definitions for whenever I use something that's not well known to the public, but it's entirely likely that I missed something. That being said, there's no reason to think that an absolute beginner to quantum mechanics or quantum computing couldn't understand what we're going to be discussing, because it'll be sort of abstract, not in the math. But if for whatever reason you feel like you missed something, by the end, feel free to ask a question. We'll have like a Q&A, and you can also rewatch. I'm recording the talk. You can also rewatch it on YouTube. And on our YouTube is also recordings of every other official event we've had. So if you wanted to learn more about other parts of QC, maybe like what qubits are, we have some stuff on that. All right, let's get into the presentation. Okay, so first things first, let's just kind of go over some terms. Most of these are pretty standard things in the quantum computing community. QM for quantum mechanics, just talking about the small scale physics, QC for quantum computer, QA for quantum annealer. Sometimes the A in QA stands for adiabatic, but basically in every circumstance I've seen, whenever it's talking about something quantum adiabatic or quantum annealer, it's basically talking about the same stuff. And then QPU for quantum processing unit, which is the quantum equivalent of a CPU. And I don't really use that too much in this talk, but I thought it would be fun to throw in because hardware, that's basically all we're talking about, is we're talking about the different types of QPUs. Okay, so this is just sort of an overview of what we're going to be talking about. First, we'll have a brief discussion of universal quantum computing versus specialized quantum computing. And then we'll get into qubit implementations, and then topology implementations, and then control implementations, and then a super brief discussion of different QC positions. And that's basically just pulled from another talk we had. I guess I should say real quick, one more thing. I forgot to talk about qubits. You probably know what it is, but qubits are the QC equivalent of a regular bit. I'm not going to get really into the theory of exactly what they are. Ben did a great job explaining it in our intro talk that we had a couple weeks ago. Again, you can go watch it on YouTube. Basically, for now, just think of a qubit as like the scratch paper that the quantum computer uses to do its calculations. But it's like special scratch paper because the quantum computer can do a bunch of calculations with each pen stroke, which is sort of the difference between a qubit and a regular bit. Okay, about QC. So what is quantum computing? Well, classical computing is sort of defined as being deterministic, error-free. That's obviously barring the super weird circumstances like when a stray cosmic ray comes in and bit flips something. But because it's deterministic, basically error-free, and it's really good for simple problems, but it gets really slow for hard problems. Quantum computing is quantum mechanically probabilistic as opposed to deterministic. It's error-prone, which means that basically the big problem that everybody has with quantum computing is trying to limit the errors that it has. Even if you get an answer to a really hard problem, if the answer is complete gobbledygook, it's not really any useful to you. And then it's like equally meh for simple and hard problems, which means it's not good for simple problems, but it's better for hard problems than a regular computer is. And deterministic is defined by Wikipedia as something which no randomness is involved in the development of future states. So if you have a deterministic model, you'll get the same output from a given starting condition. So basically, we can perfectly predict how the machine will operate. Bottom line is, by using QC, we trade determinism for errors, but in return, we can solve significantly harder problems. And that asterisk is there just because the theoretical advantage, let alone the physical, like actual implementation, is difficult to prove conclusively. And for a lot of problems, kind of an open question. So take everything we say about quantum computers, the future, kind of with a grain of salt, because it's like everybody hopes that that's true, but it's really hard to actually mathematically prove that, and not even talking about physically implement it. Okay, so getting into the real stuff here. Universal versus specialized QCs. Okay, so there's sort of two general definitions that people can mean when they're talking about a universal quantum computer. One is the Feynman-Deutsch universal quantum computer, which is basically talking about you have one device that integrates a classical computer in a quantum computer together. And so then it's universal because it handles every computation. It's like the computer you go to for any problem you ever have. The stuff that classical computers are good at, it's good at because it has some classical computer stuff. Things that quantum computers are good at, it's also good at because it has some quantum computer stuff. There's sort of like three necessary qualifications that you could have to be Feynman-Deutsch universal. You need to have like qubits that have a universal quantum logic gate set, which basically just means a set of logic gates that can perform any logic operation. You need to be able to simulate or implement anything that a classical computer can do. And you need to be capable of simulating physics, because that's sort of, at the end of the day, the entire thing everybody wanted to do with quantum computers. And then there's kind of like a fourth, it's not really optional, but it's like would be preferred requirement for Feynman-Deutsch universal. And that's talking about you would want this scale of problems it can handle to be up to and maybe even including big data. So then the other type of universal quantum computer is the what I'm calling the modern corporate universal. I think I also call it modern consensus later. I'm talking about the same thing, but so all this is it's basically what companies have agreed to call like this is their definition of universal, and really all they're talking about is that you have a universal quantum logic gate set. They're not talking about integrating the a classical computer and a quantum computer together. And so they're calling it universal because it can handle a wide range, and at the end of the day, what they're trying to get to is a universal for like all types of problems. So that's just to say, basically, there's two different definitions of universal. It can be a little unclear which one people mean when they're just sort of bringing it up. Okay, and then specialized QCs. So specialized quantum computers are kind of the opposite to the modern corporate. So the modern corporate are talking about having universal quantum logic gate sets. You need to have the modern corporate and at the end of the day get to the Feynman-Deutsch, but the modern corporate isn't everything that you need. The sort of modern corporate universals are more powerful in the long run, but they're much slower to develop. And as you can see here, like IBM just released their 127 qubit Eagle, but D-Wave already has a 5,000 qubit Pegasus. So there's significantly more power in the specialized quantum computers. However, they're not universal. They don't have a universal quantum logic gate set, which basically just means they can't do every problem. So they're powerful, but only in the specific problems that they're made for. Okay, qubit implementations. Okay, superconducting qubits. So basically all superconducting qubits are built upon Josephson junctions, which is just when you have two superconductors that are weakly coupled. And there's a few different ways you can do that. You can do it by separating them with an insulator. You can do it by separating them with a short non-superconducting section. Or you can do it physically by somehow it's the same superconductor all the way through, but you restrict its superconductivity at the connection point. And Josephson junctions work by there's the quantum tunneling of Cooper pairs through that little barrier. So I'm going to give a brief description of what those two terms are. So quantum tunneling is a purely quantum phenomenon that wave functions, which is generally just a technical way of saying particles, can penetrate through small barriers. The simplest example to understand this is as follows. Imagine a ball rolling on the ground towards a wall. Classically, we know the ball will hit the wall and not pass through. It'll bounce off or maybe just stop. In quantum mechanics, though, and because it's quantum mechanics, we know our ball is really tiny and our wall is extremely thin. There's a probability that the ball will pass right through the wall. That probability, which you could call the probability of tunneling, is directly related to the thickness of the wall and the speed, or more accurately, energy of the ball that's rolling. The faster the ball, the higher the probability, and the thicker the wall, the lower probability. And then Cooper pairs are the most widely accepted mechanism for superconductivity. In the most well-understood circumstances, Cooper pairs are pairs of electrons that link up to form a single particle. This is what we'd call a composite particle in particle physics because it acts like a single particle, but is actually made up of multiple fundamental particles. Protons and neutrons are another example of these. These Cooper pairs of electrons then all link up together and act as a single particle, but for some reason we don't call that its own single particle, and why I couldn't tell you. And then, so the flow of these Cooper pairs is then called a supercurrent. And in reality, Cooper pairs don't have to be electrons, and the mechanics of exactly how they form is not well understood, except in the simplest of circumstances. There's a ton of research going on trying to understand weird superconductors, like copper oxide superconductors. But in order to sort of stay on topic with the talk, I'm going to leave any discussion of that to the Q&A section at the end. Okay, so there are three main types of Josephson junction qubits. The charge qubit, the flux qubit, and the phase qubit. The charge qubit define the qubit basis states by the amount of tunneled Cooper pairs in the island. And after this slide, I'll go ahead and show images of what the circuit diagrams of each of these look, and it'll make a little more sense. But so the charge qubit defines the basis states by the amount of charge. The flux qubit defines the basis states by basically opposing currents. And the phase qubit defines the basis states by the frequency of phase difference between two superconductors. So you can imagine you have two superconductors and there's the wave functions, there's some oscillation between the two across that Josephson junction, and the phase difference between those two superconductors are that's the basis states for the phase qubit. Now you might have heard of transmon qubits before, and transmon qubits are basically just charge qubits, but in a different regime. So a charge qubit is, let me go to the next page and show you the picture. So the charge qubit is in the top left here. And you can think of it as just being that U is just any sort of potential. So pretend it's a battery and it's hooked up to a capacitor. And then that box with an X in it is the Josephson junction. And the island is the part of the circuit that's in the dashed box. And so the typically the energy stored in the capacitor is much larger than the energy it takes to cross over that Josephson junction threshold. And if that's true, then you are in the regular charged qubit regime. However, if the Josephson junction energy is much larger than the energy stored in the capacitor, meaning it takes way more energy to cross over that Josephson junction than you have stored in that capacitor, then now you're in the transmon regime. And transmons are kind of interesting because that's what a lot of the big companies are using. Google's QPU called the Sycamore has transmons. IBM's the Eagle has transmons. So transmons are very popular, basically. But anyways, so looking at the other two, the simple explanation for how they work is the top right is that phase qubit. You can kind of pretend that the phase qubit is it's not really pretending, but you can simplify it as to think that the phase qubit is current controlled. The charge qubit is voltage controlled, and the bottom is the flux qubit, and it's sort of inductor controlled. So it's kind of, you just have different like sort of classical ways to control a circuit, and it's just different, using different ones of those with a Josephson junction, and that's how you get the three different types of qubits. So there's another key thing that I should talk about here, and that's to make a universal quantum logic gate set, which is the key component for the modern corporate universal quantum computer. You need to define both single qubit rotations, meaning taking one qubit and changing it from one state to another, so from a 0 to a 1, and also like 2 qubit interactions, multi-qubit interactions, which is just that you change one qubit and it affects another one. So in the superconducting, the superconducting quantum computers, the single qubit rotations, meaning just the regular bit flips, are achieved through microwave pulses sent to an attached antenna, whose resonant frequency is near the energy difference between the two states. So basically all that means is that you pretend you have a little line coming off from like the Josephson junction, and the line vibrates at a frequency that is basically resonant, is the same energy as the energy difference between the 0 state and the 1 state. And so it flips the bit. For the 2 qubit interactions, the way you implement it depends on how you couple the qubits, which is also dependent on the topology of your overall quantum computer. One coupling strategy is to connect the qubits with a traditional circuit and tune their coupling strengths based on how aligned the qubit resonant frequencies are. So basically you have 2 qubits and you put a regular wire and other things, but just think of it as a regular wire between the 2 qubits. And depending on how close the resonant frequencies of the 2 qubits are, tells you how coupled they are. So if they are very far apart, then changing the resonant frequency of one isn't really going to change the other one, because it's not even close to being the other one's resonant frequency. But if the resonant frequencies are really close, then they're very strongly coupled. This design is really simple because it uses regular circuits, but it limits the quantum computer to neighbor-only interactions, meaning every qubit can only interact with the ones that are directly next to it, because you have to physically link them with a regular circuit. And this limits the overall connectivity you can have of your quantum computer, which, as we'll see later, is important. Another strategy couples qubits via a quantum bus, but the only reason it's called a quantum bus is because it's encoding the quantum information from one qubit and sending it to another, and so it feels like all couplers should be called that, not just these. But anyways, the quantum bus is often implemented physically through a microwave cavity, which is just basically a really small harmonic oscillator whose resonance is in the microwave region. And then the qubits can then be tuned both to each other and the bus, that microwave cavity, which is important because now that you can tune those 2 qubits to an outside third member, you can start tuning other qubits across the quantum computer to that outside member as well, which means you can suddenly, you no longer are limited to just neighbor interactions. So it's more complicated to implement the quantum bus, but at the end of the day, it's better in the long run because you can get more connectivity. So here's just a graph of some of the different qubit types, the superconducting qubits. All the circles are those Josephson junction qubits, and then plotted against the time, which is basically when they were developed. And then the lifetime here is talking about the essentially the time before the qubits decohere. And so to talk about what that means, so coherence is essentially the amount of time that the quantum computer has to solve a problem. Once a quantum computer decoheres significantly, meaning a large number of its qubits have decohered, the answer it'll give will be random and not useful. Specifically, the decoherence times are measured as the time for about 63% of the qubits to decohere. That percentage is derived from 1 minus 1 over E. So notice that as time moves forward, the decoherence times are getting longer, but the longest time reached by superconducting qubits is still in the single digits of milliseconds. So we're still quite a long ways to go from really getting long stage quantum computers. And I mean, compare this to like regular computers, we never have to worry about them decohering. Like if you run a program and it takes 10 days, well, that sucks because you don't have your computer for 10 days, but there's no problem with that. Here, it's impossible. You can't do it. And then you'll see that there's sort of T1 and T2, and those are two different measurements for coherence time. If you've had any experience with NMR or MRI, you might have run into those before, and they're the same. So T1 is also known as the spin lattice relaxation, and it's the time it takes for an excited proton to realign with an external magnetic field. And T2 is known as spin-spin relaxation, and it's the time it takes for an excited proton to fall out of phase with other protons spinning perpendicular to the external magnetic field. And if all of that was sort of like over your head, that's totally fine. Just think of it as there's a couple different metrics from which we can measure coherence time. It's not just one number. Okay, now we're going to talk about trapped ion. So trapped ion, typically you'll use the Paul ion trap, Paul just because that's the name of the guy that developed it. And you essentially use radio frequency EM waves to lock ions, meaning atoms that have had some of their electrons knocked off, into like a 2D plane. You have to use like waves because you can't trap ions with electrostatics. There's this guy Earnshaw, and he has a theorem about it. If you've taken higher EM classes, you'll have heard about it. If not, there's a book, Griffith's Introduction to Electrodynamics, and he does actually a pretty good job explaining it. So if that's interesting to you, you can look that up. So then after you've trapped the ions with these radio frequency waves, you supercool them until their vibrations are quantized. The quantizations of the vibrational energy are called phonons. They're quasi-particles because they're not really a real particle, but it's a quantization of like some energy. So we pretend it's a particle and we treat it as such. Anyways, that's not super important. I just think it's fun. And so once you've trapped the ions, there's two main ways to form qubits out of them. There's hyperfine qubits and optical qubits. So hyperfine qubits define the qubit basis states between extremely small differences in energy states of the ions, and optical qubits define the basis states by the ground and the first laser excited state. So you can think like the typical, when you think of an atom and you think of the excited state, like an electron goes up, that's like the typical optical qubit, versus the hyperfine qubits, you're dealing with the 0 state and the 1 are much smaller and much closer together. So hyperfine states refers to small shifts in an atomic energy due to interactions between the nuclear magnetic moment and the magnetic field produced by the atoms surrounding electrons, as well as the interaction between the nuclear electric quadrupole moment and the atomic charge distribution. So to give some context, the hyperfine structure is at its largest around 2,000 times smaller than the regular excited state distributions of electrons. So significantly smaller energy differences than in the optical qubits. Oh, sorry. Okay. So hyperfine qubits, it requires, you have to have ions with non-zero nuclear spin, because obviously that's how you get the hyperfine energies anyways. The benefit of them is you get coherence times up to like 10 minutes, which is huge. I mean, especially when we think about the superconducting qubits from just a couple minutes ago, the highest we got there was like 1 millisecond. And we're talking about 10 minutes here. So significantly larger. It's probed with this technique called stimulated Raman transitions, SRT, and Rabi oscillations. I'm sure I'm not pronouncing those correctly. But basically, to describe what they are, so hyperfine qubits use lasers by irradiating the atom with the light of an approximate wavelength of the energy gap between the ground state and a higher excitation electron level. So like the regular sort of electron excitation that you're used to. However, if the qubit is in the up state, meaning it's not in the ground state for the hyperfine, it'll be at a different enough energy level that no electrons will be excited. So therefore, the amount of light released by the atom when you irradiate with that wavelength will be basically close to zero. And how much light that you get out, how much light is re-emitted by that atom after you irradiate it with this laser, tells you what state it's in. So this cycle of absorption and emission is just called Rabi oscillations or Rabi cycles. But when things are referring specifically to the cycles or specifically to energy excitations that relate to hyperfine energy gaps, that's where the stimulated Raman transitions or SRT comes in. So optical qubits are similar, but you don't have to have non-zero nuclear spin. You just need to have ions. The coherence time is 1 second, which is worse than the hyperfine, but still quite a lot better than the superconducting. And they're also probed by Rabi oscillations, but not the SRT because it's not hyperfine. Yes. Okay. So with the Rabi oscillations, this allows us to get bit flips because we can basically probe, we can shoot the ion with just the right amount, just the right wavelength light and flip it from a 0 to a 1 or vice versa. But the problem here is then how do we define a multi-qubit interaction? So in hyperfine qubits, the coupling is carried along the Coulomb interaction, meaning the qubits are actually, like the ions are actually coupled through the Coulomb force, but the Coulomb force itself is not the coupling because the nuclear states are independent of any Coulomb interaction. So you basically need to devise a way to connect the Coulomb force, which is what connects two ions together, to the actual states in the ions. In optical qubits, the energy difference between the two states is large enough that you will actually get some motion from the optical qubit being in a larger state. And so it'll just naturally interact with the neighboring qubits through the Coulomb force. So this isn't a problem. So the two main ways of coupling hyperfine qubits are motion sensitive SRT. That's that stimulated Raman transition again, and qubit state dependent forces. So motion sensitive SRT, you send two Raman beams where the Raman beam is just a beam of light that is at the correct frequency to cause Raman transitions. So you send these two beams of light at two ions such that the beams of light that you're sending have a vector difference in the direction that you want to couple. So essentially you're just imparting momentum such that there is some interaction in a certain direction between these two ions. And And then if the beams are tuned to the carrier transition, which is the frequency that causes rapid Rabi cycles, rapid Rabi oscillations, multi-qubit entanglement is possible, meaning you can have more than two. And you don't need to actually have motion in the ions to change their state when you have the light beams tuned to the carrier transition frequency. The other way that you would do it is that qubit state dependent forces. That's a really stupid term, because that's basically everything you're trying to do is you have a qubit and you have the Coulomb force, and you're trying to make the Coulomb force state dependent so that you can have interactions between the states of the qubits. So to call it the other thing we do is qubit state dependent is you're just vaguely describing the entire point of what we're doing. But another example that you could use is basically use lasers to maybe create a dipole force that depends on the spin of the ion. And then obviously, depending on what state the ion is in, the dipole force is different, and that means that it's pushing on its neighboring ions differently. There's lots of different ways that you could potentially do it, and a lot of research going into new, maybe better ways. But yeah, those are just some examples. Here is an image of the Hyperfine qubit. So you can see the F equals 1 is at the very bottom is the down state, and the F equals 0 is the up state. And it's a pretty small energy gap between the two states. Especially when compared to the optical qubit, where it was a little unclear from the paper I was reading exactly which energy gap it's defining as the down and up. It doesn't have the nice bracket notation, but I think it's saying I think it's saying maybe from the floor up to P1/2, just because of the arrow that it's unidirectional. That's sort of what it seems like it's saying to me, but I'm not sure. Anyways, regardless, it really small energy differences on the Hyperfine, and not as small on the optical. Okay, topology. So we'll start by talking about, this will be a kind of less technical. There'll be more pictures in this one. Google Sycamore. So Sycamore is Google's QPU. It's their big big thing that they've been doing. It's the thing that they used to claim quantum advantage. And so it's a simple square lattice. Each qubit is only coupled to its 4 neighboring qubits, and they're coupled through that microwave cavity that we were talking about earlier. This is what it looks like. It's pretty boring. Pretty much like the easiest, if you're talking about, okay, I have some things on a 2D grid, how do I connect them? You just draw lines directly between the points. That whited out qubit at the top is because at the time that they did this paper, which is when they were actually doing the Sycamore test, that one qubit wasn't working, so they just wanted to denote that in the paper by changing its color. And then IBM heavy hex, it's a hexagonal lattice. Again, neighbor only connections, but it's a little worse on connectivity. Each qubit couples with only 3 others, and again couple through the microwave cavity. So this is what that one looks like. The blue is the couplers, and the green and purple are the actual qubits. And IBM claims that by setting up their lattice this way, as opposed to, I think before they were doing a square lattice, they're claiming that even though they've decreased connectivity, it's significantly decreased their errors as well. So they're basically saying, hey, even if we can't do as many problems, the problems that we can do, we're much better at. I didn't look into how much that is true. I just basically read their website and said, okay, that's what they say. But yeah, that's their claim anyways. And then we have D-Wave Pegasus. So D-Wave is a really big company. They do both hardware and software, but their stuff isn't the quantum computers, it's the quantum annealer, which you might remember from the very beginning when we were going over the different acronyms. And so their lattice structure looks quite a bit different than the regular, like the really standard Sycamore and kind of standard heavy hex. Each qubit couples with 15 others. They had an older version called Chimera, which is like their last generation topology that each qubit coupled with 6 others. And also the couples are through traditional circuits, which, as you might remember from earlier, basically means it's simpler to build, which is probably why they have so many couplings. But they're stuck in only doing neighbor connections. But all of the companies are doing neighbor only, so maybe it's been working out pretty well for them. So the top left there is the Pegasus graph. Each of those highlighted sort of bars is a qubit, and the bottom right is the Chimera graph, where again each one of those little like loops, they call them, I think they call them loops. They always feel like rubber bands to me, like rubber bands around little wooden posts. But anyways, so the coupled qubits represented, this is for the Pegasus, represented as horizontal and vertical loops. The horizontal qubit in the center, shown in red and numbered 1, with its odd coupler and paired qubit, also in red, is internally coupled to vertical qubits in pairs 3 through 8. Each pair and its odd coupler shown in a different color, and externally coupled to horizontal qubits 2 and 9, also shown in a different couple. So basically, all they're saying there is just because of the way that their system is set up, they're calling like the coupling between 1 and 3 as a vertical coupling versus a horizontal coupling that it's doing to 2 to 9. And then this one tiny little red line there between sort of the 2 red bars is the odd coupling. So you count up all of the, you look at this top red line and you count up all the ones it's connected to, and you'd get 15. So the bottom right is the regular Chimera cell, which the Pegasus is built on. I didn't get the picture for it, but if you look at it, you can kind of see that it looks like the Pegasus, the Chimera graph is like hidden in there, and it is. They did this intentionally. But the Chimera graph is sort of the same way. So each of these loops is a qubit, and like this one is horizontally coupled to this green one in the middle is horizontally coupled to a blue one on the left and right, and vertically coupled to 4 black ones, which gets you to a total of 6. So why is QC topology important? So first is problem generalization. Topology kind of determines what problems are possible to run on your quantum computer. You can kind of think of this as in, if somebody didn't give you a computer, but they gave you logic gates, but they only gave you like certain ones or a certain amount, there would be some problems that you just couldn't do because there would be no way you could represent them with the tools you were given. So that's sort of that point. And both forms of universal, both the modern corporate as well as the Feynman Deutsch, will eventually need fully connected qubits, which none of which we've seen so far has been. It's all been like Google had 4, each qubit couples to 4, IBM had 3, D-Wave is crushing it with 15, but we're still nowhere near. They had 5,000 qubits in the machine, and each one is only connected to 15. That's, you're miles away from fully connected. The other reason topology is important is because of error correction. So the topology kind of determines what types of error correction you can run. You sort of need a different error correction scheme depending on the topology of your quantum computer, which is why everybody is always trying to find new error correction schemes. And some topologies actually have error correction and fault tolerance built into them. So that would be sort of an added benefit of a certain topology. Okay, the last sort of dense part, control implementations. So there's sort of 2 different ways that you could control a quantum computer as we have now. There's gate-based quantum computers, which is the most common, and then there's like the quantum annealer, which I think only D-Wave, that's the only one I know about. Perhaps other people are doing it. So gate-based quantum computers, they use quantum gates. Wow, so surprising. And basically it's just that you're using qubits and arranging them into circuits very similar to how you would classically. And then you compute things by running your circuits and controlling your qubits with those logic gates, exactly how you would, if you squint your eyes, exactly how you would like with a classical computer. A really common gate that you have is a controlled NOT gate. This is a super common one to use if you're going for the universal quantum logic gate set. And there's a theorem, and I don't remember the guy's name. It's not like Da Vinci, but it's kind of close. But he basically said that if you have a C0 gate and then single Da Vinci, yeah, and then single qubit rotations, with those 2 things, you can fully describe a universal quantum logic gate set. So a lot of what people do, like in both the ion trapped as well as the superconducting qubits, they'll use them to make C0 gates. So gate-based is the much more powerful one out of the 2 implementations, the 2 control implementations, and it's the I said modern consensus, but the modern corporate universal. It's the one that you need for the modern corporate universal, but it's a lot slower to develop. As of now, those sorts of things like IBM and Google, they're still kind of just toys. Versus the D-Wave quantum annealers. So they're called annealers because they work very similar to annealing in metallurgy. And so what you do is you basically initialize the quantum computer into like a very simple programmable state, and then you like slowly flip qubits as you evolve the system. And you do it with some penalty that you're like pretending, oh, this computer is cooling down. So at the beginning, there's a really high chance that you're gonna have a bunch of random flips of bits. And then at the very end, it's like, oh, the computer is cold. So it's only gonna flip a bit if it really gains, like if it really goes to a lower energy state when it does that. So quantum annealers obviously don't require any gates. And the evolution of the system and the flipping of the qubits is entirely determined by that energy favorability. And so the idea is that the system sort of finds the lowest energy state as it evolves, or that's at least the hope. It's the less powerful one of the 2 control implementations, and it's really tailored for optimization. But it's a lot faster to develop, and that's why D-Wave has so much stronger computers right now, quantum computers. So that asterisk there at the end of the adiabatic theorem point, it's basically just there because in practice, like in theory, the adiabatic theorem would ensure that we always get to the ground state of our solution, but in practice, that's not necessarily always true. There can be some thermal excitations or just like regular errors that quantum computers are dealing with. So that's not always true, and you sort of have to work around it, but yeah. So specifically the type of optimization that D-Wave's quantum annealers can handle are called quadratic unconstrained binary optimization problems, or QUBO for short. So the quadratic refers to the fact that the highest order interaction amongst qubits must be pairwise, or said another way, the highest order interaction amongst the problem that you're describing has to be pairwise, has to be squared. The unconstrained means that your system doesn't have any outside constraints beyond the parameters you describe, basically beyond the things that you're telling it has to constrain, which is just the problem that you're giving it. The binary means that you must be optimizing between two choices, and the optimization is, of course, referring to the fact that you're trying to find an extrema, for example, the max or the min of your problem. So that's sort of the end of the tough stuff. From here, there's a few slides that I unapologetically stole from our talk we did last year, last spring quarter, on QC and industry. So as I'm going through these, I'll just sort of slowly flip through them. If any of this looks interesting, I'm going to post the link for that specific video in the chat at the end, which is to our YouTube that has that video on it. And even if this stuff doesn't seem super useful because you've just seen the slides, there's like an hour-long talk we did with somebody who was in, I think he was global outreach chair for IBM. And so he sort of talked about his experience in the quantum computing industry. So yeah, so full stack quantum computing, those are the companies that do software and hardware. Just because it's pretty rare to only be doing hardware for quantum computing. You know, IBM, Google, those are the big ones. And there's a few other small ones across the globe. Job qualifications, it sort of ranges, but you'll see a lot of master's degrees, PhDs. They like backgrounds in quantum physics. They also like backgrounds in computer science. Who would have guessed a field that's like the combination of the two? And it kind of ranges. I think the more software ones, yeah, so the more software quantum computing jobs tend to be more like you need a bachelor's, prefer a master's, and then experience in CS with maybe some knowledge of hardware, versus hardware is like you need a master's and maybe a PhD, and then you need a knowledge of like hardware, and if you have some experience with software, that's good too. So I have one last slide here. So it's just sort of a summary of what we went over, because I know it was a lot. So there's three main ways to distinguish quantum computers: by qubit implementation, topology, and control method. For qubit implementation, the two that we went over are superconducting qubits and trapped ion. There's a bunch more. There's photonic ones, and people are trying to come up with new ones all the time. And then, you know, even under those distinctions of qubit, you know, like the trapped ion has the two different versions. The superconducting has 3 different versions we talked about, but actually a ton. So there's a bunch under, there's like a lot of subcategories under these 3 to distinguish quantum computers. And then in topology, it's sort of like every quantum computer has a slightly different topology. So there's definitely no way we could cover all of them in this slideshow. And then control method, as of now, so far as I know, really the 2 big ways are the quantum gate and quantum annealing. So in general, fully connected modern consensus or modern corporate universal is the industry goal. That's what everybody is looking towards. But once we reach there, I think that we will be pivoting towards the Feynman-Deutsch universal, so sort of integrating classical computers and quantum computers. And as it stands today, the most general and powerful, which is, you know, the prospective powerful quantum computers, are just toys. So that's like Google's and IBM's are really kind of just toys. While the less general and more specific quantum computers, like D-Waves, are beginning to have use. People are actually doing like real research, real work using them. And this is sort of what defines the noisy intermediate scale quantum, or NISQ, era that we're in. So if you've ever heard anybody use the term NISQ, that's what it means. And all it's basically saying is that things are cool, but they're still not particularly that useful. So yeah, after this, I have, I think, like 5 slides of bibliography. So I went ahead and whenever I use something that I got from a source, I put the number next to it. So I'll post the link to the slides in the chat as well. And you know, like if any of this you wanted to read more about, it's all here, all the links to stuff. And it's a lot of Wikipedia, but I would encourage you to not be put off by that. You would be amazed how much Wikipedia is helpful when you're like trying to learn really niche science topics. It's sort of like if you're talking about something very esoteric, your 2 options are read actual research papers in it or read the Wikipedia article. So it's not too bad when you think of it that way. And it'll give you some background into the topic. So yeah, questions. And it could be, if you want like a more in-depth talk on anything I covered, you want me to go back and re-say something because I went too fast, literally whatever, and I'll go ahead and we can talk about it. And I also went ahead and posted in the chat, it's a link to these slides, which I put a lot of work into. So if you wanted to go back and check them out, I would really encourage you to. The link to our Discord, which is sort of where we get all the information out to people in the club, and a link to our Facebook. But yeah, I'll be here till 5, and I could say a little after. So if anybody has any sort of questions, don't feel free to ask.
Do you actually think that quantum computers will ever get as prolific as your regular like PCs are today, or do you think they'll always remain like specialized machines?
I don't know. If you asked me this before I really got into the research for doing this presentation, I think I would have said no. But basically with the idea that quantum computers are only ever going to be like a cloud thing. It's just like somebody in some basement somewhere has a quantum computer and like half the world can connect to it and do whatever they want on it, which I think is certainly going to be true. But I'm not so certain anymore that there is no way that we could ever make them more accessible. I kind of think we might. There might come a day that we do make them more accessible. There was something I was reading the other day, and it wasn't quantum computers, but it was talking about like particle accelerators that are the size of a microchip, which like that seems completely ridiculous. That seems just as ridiculous as having like if you had a personal quantum computer. So if they can make microchip sized particle accelerators, I don't doubt that they could make personal quantum computers.
Wait, I actually kind of wanted to add something to that if you guys have a second. So I don't know if you guys are on the Discord, I posted something about a silicon-based quantum experiment that they were running, which is for a lot of people that's kind of the goal eventually, is to have something that can run on silicon and use the same fabrication that we already use for like all our CPU devices and all that stuff. And so that device they're talking about, they were saying they were able to keep a qubit with like a 35-second coherence time, which is just totally ridiculous, with over 99% fidelity, which would be like a less than 1% error rate, right? So if we could eventually get that silicon technology to work, like just run these things on semiconductors, it very well could be possible to have one like in your phone or something like that. So that's kind of something that would be interesting to look out for. I don't think anyone's really done silicon that well. The way that Google's have been able to actually do useful stuff. I don't think anyone's done that with silicon yet, but we'll see. Maybe that'll become in your phone or something at some point.
Yeah, I remember you posted that. I hadn't gotten a chance to read it yet. That's bizarre. That's like insane. They were able to do that on just some silicon.
Just the parting thought, don't you think there's some kind of just wondering like about the philosophical issue of like having them so widespread that anyone can access like a quantum computer? That's a lot of power to give any single individual, don't you think?
Yeah, that's probably true. I was thinking about this the other day in the context of like the horrible crypto stuff we're dealing with. And I don't mean that just in terms of like NFTs and crypto because it's stupid, but like ransomware, like cyber attacks are up really, really high. And if you get hacked now and they like lock your files, you could conceivably be like, oh, well, once a quantum computer comes around, it can break the RSA encryption, I can get my files back. But if they were able to encrypt it with like quantum because they had access to a quantum computer, you would be screwed. So I was thinking about that and I was like on the positive, you'd be able to break. The good thing about having everybody have access to it is no longer people would be able to ransomware with RSA. The bad thing is now they would ransomware with quantum and then you would be really, really done.
Yeah, so I don't know if it would be, I'm just thinking in my mind, would it be a really good thing if it became widespread or a really bad thing? So I know even with computers today, like you said, we have a lot of ransomware and a lot of bad things that goes on with them because it's so widely accessible, and then we just add an extra layer of like power to that. It's hard to say what's it's gonna benefit the world or it's gonna actually go the other way around. Never really know.
Yeah, no, I think you're right. It's definitely an open question.
Anyway, thank you for the presentation. It was enlightening.
Yeah, thanks for coming.
Was it good, Tommy?
Hold on, I can't talk yet.
You can stop recording now.
Yeah, I know. I have to stop recording.
This is gonna make